ECOM 3313, Lecture 3, Phasor with solutions to the telegraphic equations and termination of the transmission lines. Now let us consider the steady state response of the transmission line to sinusoidal excitation. If you refer to the figure, this would be the transmission line in the sinusoidal steady state. So transmission line is denoted by these two lines here. So you will have the voltage source and then the source impedance, and at the end of the circuit you will have the ZL, which is the load impedance. So we derived in the previous lecture the wave equation for the voltage and current as equation 1 and equation 2. So it looks quite complicated. So for sinusoidal steady state, we're going to employ the phasor representation of the voltage and also the current. So we call this as spatial phasor function, the Vz and also the Iz. So equation 3 will give you Vz exponent j omega t, and also for the current Iz exponent j omega 3. So if you substitute equation 3 into 1, this will give you equation 5. So we're going to simplify equation 5 further with beta is equal to omega times with ZLC as the phase constant for reasons that will be apparent shortly. So the L and also the C are the usual transmission line per unit length parameters. We're going to consider the inductance and also the capacitance. So from that equation, from equation 6, we are going to insert it into equation 5. So we have here beta squared is equal to omega squared LC. We're going to get rid of the square root. So this will give you omega squared over Vp squared. Now substitute that will give you equation 7, and also after that you can also apply from equation 4 and 2. You can also derive for the current, and this will give you equation 8. So equation 7 and 8 are the wave equation for V and I in the frequency domain. Now, the constants I0 plus and also I0 minus can be expressed in terms of V0 plus and V0 minus. So you have I0 plus is equal to V0 plus over Z0, while I0 minus will be equal to minus V0 minus over Z0. So if we substitute these two equations into equation 10, we will find that Iz is equal to V0 plus over Z0 exponent minus j beta Z minus V0 minus over Z0 exponent plus j beta Z. And also for the voltage, we will have, it's much simpler, Vz is equal to V0 plus exponent minus j beta Z plus V0 minus exponent plus j beta Z. So these two equations should be committed to memory. They are the general form of the phasor voltage and also currents on the transmission line. Right. So in the last lecture, we have mentioned that the transmission line could be used to model the voltage current on any structure that supports TEM wave only, the transverse electrical magnetic wave. So what changes from structure to structure are the values of the L, C, R, and G. Okay, so you can play around with the values of the LCRNG. So consequently, the values of Z0, Vp, beta, and also alpha will generally change from one transmission line to another. So the numerical values can also be changed within a type of transmission line by varying the dimension and construction material. So what you have to do is just play around with the dimensions of the material and also what it is made of. Next, let us look into the termination of the transmission line. So we will now consider the termination of TLs that are excited by sinusoidal steady state source. So you have the TL here, okay, by these two lines, and then you have the Z load. So for mathematical convenience, we will consider Z is equal to 0. So adding termination would produce reflections. So the keyword here is reflection. So the total voltage and current anywhere on the transmission line would be the sums of the forward and the reverse of the propagating wave. So from equation 13 and 14 that we have seen before, the voltage on the current on the transmission line, we have the form of these two equations. Okay, we have seen this one. Now, the lump load ZL that terminates the transmission line is considered a boundary condition. Okay, the lump load, the impedance load. Okay, so this will give you V, Z is equal to 0 is equal to I, Z is equal to 0 times with ZL. So now we can solve for V0 minus in terms of V0 plus by applying the boundary condition. So solving for V0 minus over V0 plus and defining this ratio as the voltage reflection coefficient at the load, we will get this symbol here. So this symbol represents the reflection coefficient at the load, equal to V0 minus over V0 plus when given that Z is equal to 0. So the reflection coefficient will equal to ZL minus Z0 over ZL plus Z0. So please remember this equation. So we're going to use a lot of this equation later on in the course. So note that in general, the reflection coefficient at the load is a complex number because your ZL is complex.